If I were to suddenly just jump out from behind a door and yell boo at you right now, you'd be surprised.
I would absolutely jump.
Right. Your heart rate would spike. You'd probably jump back a foot or two, maybe drop whatever you're holding. It's this very visceral emotion. It's messy, it's physiological, and it is just a deeply human experience.
Yeah, and it's also a completely subjective experience. Like, you can't look at someone who just got jump scared and say, yes, my sensors indicate you were exactly 4.7 units surprised by that.
Exactly. But what if you actually could? What if surprise wasn't just this fleeting feeling, but a cold, hard, mathematically rigorous metric? Like a specific number you could calculate to the decimal point to measure exactly how confused or uncertain or just utterly blindsided a system is.
It does sound a bit like science fiction, right? Attempting to quantify confusion.
It really does. But today, we are looking at the secret, invisible metric that dictates how every single artificial intelligence on your phone actually thinks. We are diving into the math of surprise.
Yeah, and yet, it is the foundational mathematics powering the language models, the predictive text, and really the AI we interact with every single day. We're talking about a concept known as perplexity.
Welcome to today's deep dive. Our mission for you today is to demystify exactly how data scientists, statisticians, and modern AI mathematically measure this concept of uncertainty. So we're going to strip away the magic of AI and just look at the hard numbers. Okay, let's unpack this.
So to really grasp this, we have to step away from the massive multi-billion parameter neural networks for a minute.
Right. Take a step back from the chat GPTs of the world.
Exactly. If we want to understand what perplexity actually means in information theory, we have to ground the concept in everyday physical reality. And surprisingly, this isn't some new AI fad born in the 2020s. It was actually originally introduced back in 1977.
Wait, 1977? That is essentially the Stone Age in tech time. I mean, we are talking about the era of the Apple II and disco.
It really is. Which just highlights how fundamental the math is. It was introduced in the context of early speech recognition by a team of researchers at IBM. Frederick Jelinek, Robert Leroy Mercer, Lola Ball, and James Baker.
Okay, so a whole team trying to figure this out.
Right. They were trying to get computers to understand human speech, and they just hit a wall. They needed a reliable way to measure the raw difficulty of a speech recognition task. Specifically, they needed to measure uncertainty for a discrete probability distribution.
A discrete probability distribution. Okay, I want to make sure we don't lose anyone in the jargon right out of the gate here. We're essentially talking about things like flipping coins and rolling dice, right? Like things with a set, countable number of outcomes.
That is the perfect starting point, yeah. The mathematics of perplexity dictate that a fair coin toss has a perplexity of exactly 2. A fair six-sided die roll has a perplexity of exactly 6.
Okay.
So generally speaking, if you have a probability distribution with exactly n outcomes, and every single outcome has an equal probability, so a 1 in n chance, the perplexity is simply n.
Got it. So if I'm trying to visualize this, if I'm, say, K ways perplexed, I picture it like standing at a crossroads.
Oh, I like that.
Yeah, like if I'm standing at a fork in the road with 3 perfectly identical paths to choose from and no signs telling me where to go, I am 3 ways perplexed.
Exactly.
If a random variable has a uniform distribution over K outcomes, it has the exact same level of uncertainty as me rolling a fair K-sided die. So if I have 20 equally viable choices, my perplexity is 20. It's just that feeling of having options, but absolutely no clue which one is going to happen.
What's fascinating here is how this connects to a broader concept called information entropy. Perplexity isn't just a basic tally of how many paths are at your crossroads. It is mathematically defined as the exponentiation of information entropy.
Whoa, okay, big words.
Yeah, I know. But basically, entropy is a way to translate that feeling of uncertainty into a concrete number based on logarithms.
Okay, entropy and logarithms.
Yeah.
Walk us through how that actually works under the hood, because, why do we need logarithms to understand a simple dice roll?
It really comes down to how we measure information itself. Claude Shannon, who was basically the father of information theory, figured out that we can measure the surprise of an event in specific units.
Okay.
And depending on the base of the logarithm you use for the calculation, the units change. If you use base 2, the entropy of the distribution is measured in Shannons, or much more commonly, bits.
Bits, like computer bits?
Exactly. And if you use the natural logarithm, base E, it's measured in nats.
Okay, so entropy tells me how many bits of information I'm missing before the die lands?
Precisely. But talking about having, say, 2.58 bits of uncertainty is incredibly abstract for a human brain to process.
Yeah, I have no idea what 2.58 bits feels like.
Right, and that is exactly where perplexity comes in. Perplexity takes that abstract entropy measurement and exponentiates it. It basically reverses the logarithm. It turns those bits back into a number that feels intuitive to us.
Oh, I see.
It converts 2.58 bits back into 6, meaning you are as confused as someone rolling a six-sided die. The larger the perplexity, the harder it is for an observer to guess what's going to happen next.
Okay, that feels incredibly clean and logical when everything is fair and uniform. A six-sided die is six, a coin is two. But the real world isn't a fair casino. Like, dice are loaded, coins are scuffed. Can this metric actually handle non-uniform situations where some outcomes are way more likely than others?
It absolutely handles non-uniform distributions. In fact, that's its primary purpose. But this is exactly where our human intuition starts to completely clash with the mathematics.
Here's where it gets really interesting, because I would naturally assume that perplexity is just a mirror image of how likely I am to guess correctly. Like, if I am playing a game where I have a massive probability of winning, my uncertainty, my perplexity should be almost zero, right?
And that is the exact trap a lot of people fall into. Perplexity is a measure of the difficulty of a prediction problem as a whole. It is absolutely not just a straightforward representation of the probability of success on a single guess.
Yeah, I actually stumbled over this totally counterintuitive math paradox when I was looking into the source material. Let's imagine a scenario where you have two choices.
Okay.
One of those choices has a 0.9 probability of happening. That's a 90% chance. The other outcome is a 10% chance. If I always bet on the 90% outcome, my probability of making a correct guess is 0.9. I would feel incredibly confident. I mean, I'd bet my house on it.
You'd assume your uncertainty is minimal. But the math tells a very different story here. If you actually calculate the perplexity for that 90-10 split, you don't get a number that cleanly maps back to 90%.
Wait, let's actually run the numbers on that. How does the perplexity formula process a 90% probability?
Well, it uses those logarithms and negative exponents we mentioned earlier. For the 90% outcome, you take 0.9 to the power of negative 0.9.
Okay.
Then you multiply that by the 10% outcome, which is 0.1, to the power of negative 0.1. And when you compute all that, the perplexity spits out a value of 1.38.
1.38. Okay, so I am 1.38 ways perplexed. But if I try to reverse engineer that back into a probability percentage, like taking the inverse, 1 divided by 1.38, I get 0.72.
Right.
That is 72%. It is absolutely not 90%. My actual chance of success is 90%, but the perplexity metric is acting like my odds are only 72%. Why is there this huge, 18% disconnect between my odds of winning and the mathematical measure of my surprise?
It goes right back to what entropy actually measures. We have to look at something called optimal variable length coding.
That sounds incredibly dense.
It does, but just think of it like Morse code. In Morse code, the most common letters in the English language, like E, get the shortest possible code. Just a single dot.
Right.
Rare letters, like Z, get these long, complex codes to keep them distinct without wasting time on the common stuff.
Okay, so you design a system that uses the least amount of energy for the most frequent events.
Yes. Entropy, and by extension perplexity, measures the expected or average number of bits required to encode the outcome using that kind of optimal code. It provides insight into the information gain expected when you finally learn the outcome.
Information gain.
Yeah, think about it. If you bet on the 90% outcome and you win, you don't really learn very much. You expected to win. But 10% of the time, you are going to lose. Yeah. And when you lose that bet, the surprise is massive. You gain a ton of information about the unpredictability of the system.
Oh, wow, I see. So the perplexity is evaluating the entire shape of the uncertainty. It's factoring in the catastrophic surprise of that 10% chance happening. It's not just handing me the raw odds of winning a single bet. It's this holistic measure of the inherent chaos in the environment I'm betting in.
Exactly. And that distinction becomes critical when scientists use this math in the real world. Because in the real world, whether we're predicting the stock market or trying to get a machine to translate French to English, the true underlying probabilities of the universe are completely unknown. We don't have a cheat sheet.
Right, we don't. So if we don't know the actual odds of the environment, how do data scientists actually use this metric?
They use it to evaluate models. Let's say there's an unknown, true probability distribution out there in the world. We'll call this true reality P.
Okay, true reality is P.
We don't know P, but we really want to predict it. So we gather a bunch of data, a training sample drawn from P, and we build a mathematical model based on that data. We'll call our proposed model Q.
So P is actual reality, and Q is our AI's best guess at how reality works.
Exactly that. Now, to figure out how good our model Q really is, we obviously can't test it on the data it already learned from. That would be cheating.
Right, it already knows the answers.
Yeah. So we have to see how well it predicts a completely separate test sample, like a fresh batch of data that was also drawn from the real world, P.
You know, this immediately reminds me of being a student. Like, think of a low perplexity model like a student who genuinely studied the underlying concepts for an exam.
Oh, that's a great analogy.
Right, so the unknown distribution, P, is the teacher's actual exam paper. The model, Q, is the student's brain, filled with the logic they developed from doing practice problems. When that student sits down to take the final test, the new test sample, if their mental model of the subject is good, they assign a really high probability to the questions that appear. They aren't blindsided.
Right. They are simply less surprised by the test sample. And mathematically, a better model assigns higher probabilities to the events that actually occur in the test data. Because it predicts well, it is fundamentally less surprised by what reality throws at it, which results in a lower perplexity value. Low perplexity models do a better job of compressing the test sample.
Compressing it, like a zip file on a computer.
Very similar, actually. Because the model already anticipated the patterns in the data, it requires fewer bits per test element on average to encode the information.
That makes total sense.
And if we connect this to the bigger picture,
Yeah.
the exponent in these complex mathematical formulas actually represents something called cross-entropy.
Cross-entropy.
Yeah, cross-entropy looks at the empirical distribution of the test sample, what actually happened in reality, and compares it to what our model Q predicted would happen.
So it's like a direct comparison between the student's expectations and the teacher's grading key.
Yes, exactly. And what that actually means on paper is defined by a concept called Kullback-Leibler divergence, or KL divergence.
Okay, KL divergence.
KL divergence is essentially a penalty. It measures the distance between two probability distributions. It calculates the extra wasted bits of information you're forced to use simply because your model Q is slightly wrong about reality P.
Okay, so if the student's brain Q is a perfect match for the teacher's exam P, the distance is 0. There is no penalty.
Yes, and that is the only scenario where perplexity is completely minimized. The divergence between expectation and reality drops all the way to 0.
Okay, we have covered flipping coins, 90-10 math paradoxes, and evaluating how well a model predicts a sequence of test events. But rolling a die or, taking a multiple choice test is one thing. How on earth does this math scale up to a whole paragraph? Like, how does this power natural language processing or the large language models like ChatGPT that are generating thousands of words in a row?
Well, in natural language processing, or NLP, we aren't just predicting a single isolated event anymore. We are evaluating entire sprawling text documents. We look at a corpus, which is a massive structured collection of texts, and a language model is essentially a probability distribution mapped over those entire texts.
But documents are incredibly messy. Like, you might have a test sample that's a 3-word text message and another that's a 300-page historical biography. How can you possibly compare the perplexity of a model on those two wildly different things?
You're right, you can't compare them raw, you have to normalize the math. And this brings us to token normalized perplexity.
Token normalized perplexity.
Right. In NLP, a token is usually a single word, or sometimes just a piece of a word. To make meaningful comparisons across different lengths of text, you calculate the overall perplexity of the document, and then you normalize it by the total number of tokens.
So we're basically boiling the AI's massive confusion down to a per-word average. What does that actually look like in practice?
There was a really famous historical benchmark for this, using the Brown corpus.
The Brown corpus?
Yeah, the Brown corpus is a collection of 1 million words of American English, compiled to cover all sorts of varying topics and genres. Back in 1992, the absolute state-of-the-art lowest published perplexity on the Brown corpus was about 247 per token.
Okay, so what does this all mean? If I'm a computer scientist in 1992 and my AI gets a perplexity of 247, what is actually happening inside the machine?
Well, think back to our dice analogy. An AI with a token-normalized perplexity of 247 is just as confused when looking at the test data as if it had to choose uniformly and independently among 247 different, equally likely possibilities for every single word it tries to predict.
Whoa, It's rolling a 247-sided die for every single word in a sentence. That
Yeah.
sounds agonizingly difficult. I mean, if you just naively guessed out of 247 options, your accuracy rate would be 1 divided by 247, which is about 0.4%. You would be wrong 99.6% of the time.
It sounds like a terrible model, doesn't it? But there is a brilliant nuance here that underscores exactly why we can't just blindly trust a single mathematical metric.
Oh, I love this part from the reading, the loophole.
Yes.
The math shows that if your perplexity is 247, naive guessing gets you a 0.4% accuracy rate.
Wow.
But if you completely throw that sophisticated model in the trash and you just program a dumb machine to blindly guess the word the for every single word in the English language, you will actually achieve an accuracy rate of 7%.
It's a massive discrepancy,
Yeah.
0.4% versus 7%, and it highlights the deeply nuanced nature of predictiveness.
Ah.
I mean, how is a blind, repetitive guess of the mathematically outperforming a state-of-the-art 1992 AI model metric?
Yeah. Why shouldn't we just build an AI that screams the all day?
Because it comes down to the types of statistics the models are actually utilizing.
Yeah.
Guessing the word "the" constantly is based on unigram statistics. Right. A unigram just looks at the frequency of single words in total isolation. The is the most common word in the English language, so purely by brute force, it hits 7% of the time. But the model that achieved the 247 perplexity score in 1992 wasn't utilizing unigrams. It was utilizing a trigram statistic.
Okay, a trigram looks at sequences of 3 words. It's actually looking at the context.
Yes, a trigram model tries to predict the next word based on the context of the 2 preceding words. It is trying to learn the actual grammatical structure, the rhythm, and the flow of the language. It isn't just firing out the most common word regardless of context.
So guessing the is extremely safe and gets a higher raw accuracy percentage on paper, but it's incredibly boring and completely useless. The trigram model is actually far more sophisticated because it's mapping the true complexity of human language. It takes risks. Utilizing trigram statistics fundamentally refines the prediction in a way unigrams never could, even if the model is still faced with 247 equivalent choices at every step.
That's the key. And obviously the field has moved far beyond 1992 trigram models. Since around 2007, deep learning has taken over entirely. Today we have these dominant transformer models, Google's BERT, OpenAI's GPT-4, all these massive large language models.
Yeah.
And token-normalized perplexity is still a central tool for evaluating them. Engineers use this metric to compare different models on the exact same dataset and to mathematically guide the optimization of the AI's internal settings, its hyperparameters.
But as these models have gotten larger and more complex, haven't researchers discovered limitations to using perplexity as the ultimate North Star? I mean, it can't be perfect.
They absolutely have. It is a powerful tool, but it is deeply flawed if used in a vacuum. First off, it's highly sensitive to linguistic features and sentence length. You cannot just blindly compare a perplexity score from a dataset of medical journals to a perplexity score from a dataset of Twitter posts and expect a perfect apples-to-apples comparison. The intrinsic entropy of those two environments is entirely different.
That makes total sense. The baseline surprise of a dense medical journal is obviously going to be different from a random tweet.
Furthermore, it turns out perplexity is an inadequate predictor of actual performance in the real world, particularly in tasks like speech recognition.
Wait, really?
Yeah, you might engineer a model that achieves a mathematically stunning ultra-low perplexity score. The KL divergence is incredibly low on the test set. But when you hook it up to a microphone and have a real human speak to it, it might still hallucinate, misinterpret accents, or just fail to transcribe accurately.
So how do they reality check the math then, if perplexity isn't enough?
Researchers often have to rely on a simpler, alternative evaluation metric called word error rate, or WER.
Word error rate. Okay, that sounds much more grounded. It's simply taking the percentage of erroneously recognized words, so deletions, insertions, substitutions, and dividing it by the total number of words spoken.
Exactly. It's a harsh reality check against the purely theoretical, clean math of perplexity. Because there is a massive danger in AI development. If you blindly optimize your system just to achieve the absolute lowest perplexity score possible, you run into severe issues with overfitting.
Overfitting, meaning the AI essentially just memorizes its training data. Going back to our student analogy, it's like a student who memorized the answer key to the practice test without actually understanding the underlying subject. They get zero perplexity on the practice exam, but fail miserably when they face a question worded slightly differently in the real world.
Right. They completely lose their ability to generalize to new, unseen information. The AI becomes brilliant at predicting the past and totally useless at navigating the future.
Wow. So to wrap all of this up, you have gone on quite a mathematical journey with us today. We started with the simple uncertainty of rolling a fair six-sided die. We untangle the paradox of why predicting a 90% probability still carries a mathematical penalty of surprise due to variable length coding. We learned how KL divergence measures the distance between a model's guess and true reality. And finally, we scaled all that math up to see how the most advanced large language models in the world measure their own confusion on a per-word basis. Next time you see an article or a headline about a brand new AI model and the company's boasting about their groundbreaking new benchmark stats, you know exactly what perplexity means. It is the AI's internal mathematical measure of surprise. And more importantly, you know exactly why a single metric, no matter how low it gets, doesn't tell the whole story of how well an AI actually understands human language.
And, this raises an important question. We've established that data scientists and engineers are constantly trying to minimize an AI model's perplexity. They are tweaking the hyperparameters so that the AI is trained to never be surprised by a sequence of human words. It should perfectly anticipate everything we say, reducing its cross-entropy to the absolute minimum. But if we mathematically train a system to ruthlessly eliminate all surprise, are we inadvertently mathematically stripping away the model's ability to ever generate truly surprising, original, or creative thoughts?
Wow, that is definitely something to mull over. Because while an AI might be rigorously engineered to be a perfect, unsurprised predictor of text, when a person jumps out from behind a door, that subjective, unpredictable human surprise is sometimes exactly what makes life interesting.